Okay, now let's talk about the correctness of our recursive functions. So just like in loops, where we have a loop invariant, the recursion has its own invariant, which we sometimes call the predicate. So similarly to the loop invariant, it takes some intuition to get the correct predicate. And once we do get a predicate that we can prove that is true, we just show the value of the predicate upon termination to show that it is indeed what we wanted to get. So don't worry too much about the recursion correctness, since this is it's relatively harder to the loop invariants. So uh, if we ever if we even ask for you to prove the recursion correctness, expect that we will be giving some starting steps or some at least some hints to do it. So you're not gonna start from scratch. Now let's have an example. So for the factorial of n, we have here a expression or a mathematical expression or formula for our predicate, which is the factorial of n is equal to the production, since if it's a sum, it's a summation. So for a product, it's a production. So the production from n or from n plus 1 minus k to n times the factorial of n minus k, where k is an arbitrary integer from 1 until n minus 1. So we prove the predicate by induction. We start with the base case at k equals 1. So at k equals 1, uh, the term at the bottom simplifies to just n. So our production is just n. And then we substitute 1 to k. So it becomes the factor n times factorial of n minus 1, which is exactly our definition of the function, which returns n times the factorial of n minus 1. Now, for the inductive step, let's have k equals k plus 1. So that means the boundary of our production at the bottom will be n minus k, and n at the bottom. Oops. So expanding this production term, we get n times n minus 1 until n minus k times the factorial of n minus k plus 1. Now, recall that without having k be equal to k plus 1, the expansion of our predicate would look like this. So it's from n up to n plus 1 minus k times the factorial of n minus k. Now, notice here that these terms here are the same as the terms over here. So that means the remaining terms here, the factorial of n minus k, should be equal to the term here, n minus k times the factorial of n minus k plus 1, which is exactly our definition here when we substitute n with n minus k. So this becomes n minus k minus 1. So n minus k minus 1. Therefore, our predicate is indeed true by induction. So now we terminate our function, and the function terminates when we have k equals n minus 1. So when k becomes n minus 1, the term below simplifies to 2. So we get the product from n times n minus 1 to n minus 2, etc. until 2. And then what we're left with here is the factorial of 1, which is our base case, which is 1. And this is exactly the definition of the factorial function, which proves that our algorithm is correct.